Hello, my name's Alex Griffiths. I'm a principal bridge engineer at Mott MacDonald, and I'm here today to talk through the design and analysis of Clifton Bridge. So this is a project that's being delivered by Skanska for Network Rail, and Mott MacDonald are employed by Skanska as the permanent works designer. The CAT-3 check-in was done by Tony G and partners, and Bramble have been involved in the assessment of the existing structure. So I'll give you a bit of an overview of the project and then talk you through the main stages of analysis and design, from concept through outline, detailed design, drawing out some of the key analysis decisions we've made, some more detailed bits of analysis we've done, which have hopefully added a bit of value to the project. So a little bit of context. Clifton Bridge is based up in the northwest of the UK, up here. It's just to the south of Penrith, next to a little village called Clifton, which is the namesake for the bridge. The bridge carries the West Coast main line over the M6 motorway, so it forms the intersection between two key transport corridors in the northwest, and will any construction works in the area will involve closing both of these transport corridors, causing significant disruption. So currently, there is a bridge there at the minute. It's a post-tensioned concrete box girder bridge that was built in the late 60s. Looks in good condition in this photo, but inside the post-tensioning tendons are severely corroded and deteriorating. There's currently a traffic restriction on top of the bridge, which sort of creates a lot of pressure to get a resolution to this structure. And remedial works were extensively investigated by Bramble, but eventually all of these were exhausted due to the required time to close the West Coast main line and the disruption to services on the line. So we got involved in the project at the start of 2024, and at which time the blockade for the installation of the works was already booked in for about 2 years later, in January 2026. So we've got a 2-year programme from the start of concept design through all the way through detailed design, construction, and bringing it into service, which is a very ambitious timeline for the project. We had a couple of months doing optioneering work and a couple of months to develop our AIP, our outline design. Both of these stages were actually done. We were supporting a different contractor, Story Contracting, through these 2 stages. And there was a little bit of a break in the design work when the project was Skanska took over the project, and this time just allowed for the contracts to be sorted. So the overall design programme is about a year, but you'll notice here that the fabrication starts in January 2025, which meant that we had about 4 or 5 months to complete the design of the superstructure and have it all CAT-3 checked and get all the details sorted so that the fabrication could start in January 2025. This was a very tight programme. And then following on from that, not long after, the precast deck units needed to be fabricated, and then again, not long after that, construction works on site started. So I'll just give a little bit of an overview of the blockade timeline. It's a 14-day blockade of the West Coast main line. We've got about 3 days at the start for preparation works. Then you've got full closure of the M6, which allows the existing bridge to be demolished. You've then got about 4 days when the M6 is reopened, while we're doing preparations and final modifications to the substructure before the new deck is installed on the second weekend, where you've got full M6 closure. And then you've got 2 or 3 days at the end to install the track and hand back. So concept design, two options were developed at the concept design stage. The one on the left is a single span truss on brand new substructures. The idea was to install these in between the abutments and piers of the existing structure, and this meant that all the substructure works could be done outside the blockade. It also means you've got brand new substructure as well, which is potentially more valuable. However, this is clearly quite visually intrusive, and there were significant concerns about the feasibility of getting this through planning. And if planning wasn't approved, what the knock-on implications would be for the already pre-booked blockade. So our second or alternative option was to do something that matched very closely to the existing structure. A steel composite box girder bridge supported on the existing substructure in a 3-span arrangement. This is more challenging from an engineering perspective, as you've got to try and demonstrate that the substructure is adequate for the new superstructure. And it also meant that there's some modifications to the substructure is required during the blockade work. But generally, as a whole, the project team agreed that this was the lower risk and better option to take forward. Okay, moving into outline design. This render here is just to give a bit of a feel for what the structure looks like. We've got a twin cell steel, weathering steel box girder, trapezoidal with sloped webs. And then we've got transverse spanning precast concrete deck slabs that are brought in and laid on top of the top flange. And the shear connection is made by an in situ pour into these preformed concrete stitches on the deck slab. We needed to introduce this central web here to comply with the track twist checks. Without this here, there's too much sagging of this deck slab, and we couldn't get the track twist criteria to be met. This slide just shows a bit of a comparison between the old deck cross section and the new structure. So the old deck was about just over 9 meters wide, and the new deck, to meet the modern envelope requirements for railways and offsets for safe access walkways, etc., sort of crept up, and it's actually nearly 12 meters wide for the new deck, which is a significant increase. And you'll remember our intention was to support it on the existing substructure, so that obviously has a knock-on consequence. And this diagram at the bottom here just shows the span arrangement. So you can see the side spans are approximately half that of the main span, which is just we just point out because it means that if you've got a point load here at the middle of the central span, you tend to get an uplift at the abutments. So this widening of the deck and this span arrangement were both indicators that we thought we would have a bit of an issue with uplift at the abutments that we'll talk about a little bit later. Okay, so our workflow for our, I suppose, design and analysis. We built a sort of geometric model in Grasshopper. One of the main reasons for doing this is that the geometry of the box girder is quite complicated. And we wanted to make sure that our webs could be fabricated from flat plates and didn't need any warped plates, which would delay fabrication, cause issues in meeting the programme for the blockade. So there's a lot of constraints for the webs. We needed them to be a fixed width at the top, so that the positions of the pockets and reinforcement for the deck slabs could be consistent as well. But because it's trapezoidal, they're sloped in at 20 degrees, and there's also a haunching of the deck the superstructure soffit, so it's haunched, and there's also a very slight precamber as well to the top cord as well. So a lot of interconnecting things going on there, and we just needed to work through and sort of convince ourselves that it could be fabricated out of flat plates, and Grasshopper and Rhino were really helpful in doing that. Another reason for wanting to sort of do this is it means I can be a little bit closer to the geometry. And with the very advanced BIM software that projects rely on these days, I sometimes feel a little bit removed from the geometry, and I felt a little bit more in control with this. Once we'd done that, developed that geometry in Rhino, we were able to bring it into MIDAS using the Civil NX Grasshopper plugin. At the time we were doing this, it was quite early stages for that plugin. So there were some issues, teething troubles with applying patch loads at the time. I think these have now been resolved. But as the project was sort of moving so quickly, we couldn't wait for those to be resolved. So as a workaround, we used a slightly different workflow where if we needed to, we applied all the loads in MIDAS Civil NX, and if we needed to make changes to the geometry, we utilised these node detail tables, which are really, really useful feature. Exported those to Excel, a little bit of conversion to get the back into Grasshopper. We can tweak our geometry as we need to, and then export the new coordinates for those nodes back into MIDAS Civil. We also created the start of our BIM model from Grasshopper. As we got further down the line in the design progress, this tie was severed, but it gave us a good head start in creating the geometry for the BIM model. So there's a couple of action effects in box girders that you don't always come across when you're doing sort of typical deck slab design, and they're both related to torsion. The first one is warping, and the second one is warp distortion or warping distortion. And neither of these are included in the sort of Bernoulli beam formulation. So if you're using beam elements in an analysis software, these wouldn't be included. So the first one, the warping, is caused when you get pure torsion. So when you get pure torsion in a box girder, you get a shear flow going around the perimeter. And if you cut out a small length of box girder, and maybe have a look at one of the flanges, say the top flange or the bottom flange, doesn't matter which, the shear flow in that flange, either end of that short section, would be going in the opposite directions. And that tends to change the shape of that flange from a rectangle to a parallelogram. And this causes I suppose if the box is not doubly symmetric, then the sections don't remain plane, and that's not necessarily a problem. It'll warp, and you'll get a slightly different shape. But because we've got very stiff diaphragms above our bearing supports, these act as restraints. So that warping can't happen freely, and you get additional longitudinal stresses in the top and bottom flanges. And these tend to be higher in the corners. The second action effect is sort of distortion. So looking at it from a cross-sectional perspective now, and again, you've got this shear flow going around the perimeter of the box girder. You can see that in the webs, the shear flow is going in opposite directions, and in the flanges as well, it's going in opposite directions. And what this tends to do is it tends to create a pinching effect. So you get two corners that close up and two corners that open up. And if you've got transverse stiffness on your webs, which we most likely will have, these will resist that distortion and attract additional load. The stiffness and both the longitudinal welds between the web and the flange need to be designed for this action effect. So the reason for mentioning all that is it informs our approach or strategy for analysing the structure. So what we've tended to do is use plate elements where these action effects could occur. So those places are basically any of the walls that form any of the walls that form the box girders. So the bottom flange, the 3 webs, and the deck slab were all modelled as plate elements, and then everything else, the top flange is any bracing members, any stiffeners, were all modelled as beam elements, just to avoid overcomplicating. And that means that these distortion and warping effects are implicitly included in the analysis. So it's quite a sophisticated analysis model, a little bit more sophisticated than a standard village model. And it's important when you do a sophisticated model, even more so than any model, that is validated against something a little bit more simple, a little bit more intuitive. So to validate our model, we created another simple line beam model where we could verify some of the key results and give ourselves confidence that the global model was behaving as expected. Once we were happy with the results, we were able to estimate what our maximum plate thicknesses were for the structure. Now, as mentioned earlier, we were expecting there might be some issues with uplift at the bearings for this structure, and this was due to the span arrangement, the short side spans, and also the widening of the deck slab at the top, while having the same width of substructure at the bottom. And uplift is generally not permitted on railway bridges in the UK. Now, MIDAS allows you to run moving load analysis very efficiently, so we're able to determine the worst case uplift scenario quite early on in the design process. And you can see here that there's about 2 meganewton uplift for our worst case. So a few key changes we had to make to try and address this issue. The first and most obvious one was to widen the bearing spacing from the 2 meters we had originally, which was obviously very narrow spacing, up to 3 meters. Now that had a knock-on consequence because we now needed to do reasonable modifications to or much more significant modifications to the substructure in order to make those bearings that much wider. That goes down to about 1 meganewton uplift, still quite a significant uplift to get to overfill. So our next step was to infill the ends of the box with mass concrete, and that helped a lot. But in the end, we needed to put a heavyweight concrete in here to ensure positive contact in all design cases. And so we used magnetite concrete, which has a density of about 38 kilonewtons per meters cubed, rather than the sort of standard 24. Now, it's worth mentioning that our bearings supports are all integrated to our node positions in the analysis model. So we utilised our Grasshopper workflow and the node detail tables in order to make some of these changes. And if the project timeline was a bit more generous, we would have maybe looked for a derogation for the uplift requirements, but we didn't think we'd be able to get one approved within the project timeline, which influence some of these key decisions. Okay, moving on to detailed design and analysis. So I suppose first off, a little bit of a look at these precast deck panels. So these were chosen mainly for their speed of installation. Even though the design, I've mentioned a few times, the design program was heavily constrained. The construction program is equally, if not more, constrained. And this meant that these could be fabricated off-site while the steel work was being fabricated as well. And then they can all be brought to site and erected in one go. So when you're dealing with precast things and getting them to overlay, there's always a lot of concern about tolerance, and we were especially concerned about tolerance on this bridge. You've got steel box girder underneath this, which is very prone to distortion during welding. Quite heavily reinforced deck panels that all need to be coordinated, overlaid, and lapped. with the reinforcement slotting in between pre-installed shear studs. So we spent a lot of time looking at tolerances, positional tolerances on the shear studs, positional tolerance on the reinforcement, the likely distortion of the box, lateral and vertical deviations at the top flanges, and any deviation in the soffit, the precast panels. And we needed to get the fabricator and the precaster both to sign up to tolerances that were tighter than those in the that are permitted in the execution standards. So we were looking for a 5mm tolerance on the placement of reinforcements and a 5mm tolerance on the placement of shear studs. And if you do that, you get we had 15mm tolerance for on-site installation between the shear studs and the reinforcement, which was something we agreed with the contractor that we all felt we could achieve. That's all very well and good in theory, but you've got steel work being fabricated in one factory and precast panels being fabricated in another factory, and a lot of effort was made by the contractor in terms of QA and coordination to make sure that everything was done as per the design. So this little image up on the top left shows a laser scan of the precast panels with a heat map of its position relative to the design position to check that they were all within tolerance. And a similar thing was done with the shear studs as well. They were all laser scanned. And actually through that process, they did identify one set of shear studs that had been set out incorrectly on the steel work, and this was addressed before it left the factory. So these photos are a little bit out of date now, but all deck panels have now been installed on the deck. As far as I'm aware, there weren't any issues, any clashes on site, so we were really, really happy with the results of that. And even though you've done all this QA, etc., you've still got the site welds to do to the steel work for the box girder, which can lead to distortion even after you've done these checks. But it all helps to give confidence that it's coming in as close as we can get. Okay, so one of the first things we did when we got onto detailed design was set up our construction stage analysis. Now, our construction stages were developed using a mixture of propped and unpropped stages, and this was to maximise the compression in the slab at mid-span and minimise the tension in the slab and top flanges in the hogging regions over the piers. So the steelwork's brought to site, landed onto trestles in a sort of fairly regular propping scenario. The steelwork is then welded up, and the mass concrete, the magnetite concrete, is then poured into the ends of the deck. Then the third stage is the first set of concrete units being landed on. And then once they're landed on and the concrete in situ stitches are poured and hardened, we can then activate the stiffness for this section, and the next set of precast panels are landed. And again, once the in situ concrete's hardened, we can activate the stiffness for those. And then so on. And then the last set of panels to be installed is just over the piers here. And by this point, sorry, I missed out the removal of the propping. After this stage here, the props are removed so that this can sag. And when these last few deck panels are installed, the steelwork is almost pre-bent over the hogging regions so that the slab is taking up minimal tension in the permanent case. So this slide is just a little bit on shear lag. This wasn't really a deciding factor in losing plate elements, but maybe just a happy coincidence or happy side effect. So shear lag is implicitly included in the results for plate elements when you model them. So I suppose if anyone doesn't know, in wide flanged members, you get a concentration of longitudinal stress at the web to flange intersection, and then that longitudinal stress dissipates as you move away from that. And you can see that here. You've got these peaks in stress that line up with where our webs are. This is a plan view of our top flange. So there's a peak in stress here and a peak in stress here. And it's just to say that these action effects are implicitly included. So one really nice feature in MIDAS, especially when you're using plate elements, is the virtual beams or section for resultant forces. And what this does is it essentially integrates the stresses over a cross section that you define and gives you the equivalent moments and forces for that virtual member. And it means you can almost design this like you would a grillage model, but you've got the benefits of being able to examine the stresses as well and the distribution of stresses across those cross sections. And without virtual beams, it would be very hard to design class 4 sections efficiently, and I'll touch on that a little bit at the next stage. And the only way I think to do it would be to limit the stress in the web so that you could achieve a compact section, which was a bit of a trick we used at the early design stage, but it's quite conservative. The plate buckling. Plate bucklings seem very complicated in the Eurocode compared to the old ways of doing it, but essentially you work out a slenderness for your cross section, and from that slenderness you work out a reduction factor. Now our reduction factor based on this was about 0.67, which means we're getting rid of about a third of our web in the compression region. Now, what you can do is you can then take that cross section, rework out what stresses you get at the extremes of your web, and then work out a new slenderness based on this iterative loop here. Now, it's quite time consuming to do that by hand, but we were able to set up a little Python script just to iterate through that. And it meant that we were able to demonstrate we didn't need to have any reduction in our webs. And firstly, that's good from a design perspective, because it means you can utilize more of the structure. But it was also really important from a sort of design practicality perspective that now, if we'd have had to use reduced sections, we wouldn't have been able to extract the stresses directly from the design model. Everything would have had to be exported based on the virtual beams, and then your stresses recalculated based on these cross sections. But because we were able to demonstrate that no reduction was required, we could then use the stresses directly from the model, and that becomes really important when you move into the fatigue checks, fatigue verification. So this slide here shows our global fatigue stresses, and as we've gone to the effort of iterating through our class 4 webs, so no reduction was required, then we could extract our results directly from the model. And this just highlights why that's important in some cases, because as you can see, there is variation in stresses across the cross section, and that wouldn't be picked up if you just integrated over the virtual beams. So it makes it easier, and also you've got a slightly more granularity on the results. Now these graphs show show the stress ranges over the length of the, I think these are both from the bottom flange. They're just shown here really just to, one thing that was quite interesting was our peak stresses at ULS were in the hogging regions over the piers, but our peak stress ranges for the fatigue were actually in the middle of the side spans, where the stress is in the bottom flange went from positive to negative, depending on whether the train was loaded here or loaded in the adjacent span. That these actually went into hogging in some cases. Now, because it's a box girder, we needed a number of openings in some of the webs and flanges and diaphragms. And these can cause stress concentrations, especially when you're designing for fatigue. Now, the PD does offer some simple factors that you can use. It's like a stress range multiplier. But even if you adopt the sort of best practice in terms of geometry, the best multiplier you're getting is a 1.8. So you're nearly doubling the stress range that you need to verify in the design. And some of these openings where we had them were in quite highly stressed areas. So there was just no way we'd be able to allow or accommodate a doubling in the stress range without going to thicker plates. And introducing thicker plates causes more problems in terms of availability and fracture toughness. So, these multipliers don't consider any additional stiffening that you might do around the opening to alleviate some of this additional stress. So we decided to sort of model these openings explicitly and refine our mesh around these openings and undertake a specific fatigue analysis. And by doing that, we're able to reduce our stress multiplier from 100%, it's probably 80%, down to around 15%. So it was really valuable going through that exercise. And sometimes when you venture out on these decisions, you don't necessarily know whether you're going to yield the results that you want. So sometimes you just you have to sort of go down that avenue. You know, it might not have been such a big saving, but we were lucky in this case that it was. So yeah, I mentioned that we wouldn't be able to accommodate thicker plates due to availability. And the other option that's often used is putting double plates on, but to reduce the stress. But again, double plates have a very low fatigue category, so I don't think it would have been particularly helpful in this scenario. Okay, so this slide's sort of just talking specifically about how we analyse the diaphragms. So above each of the bearing locations, we've got a full height diaphragm across the whole cross section. Now the PD, I think it's PD 6695 part 2, has some closed form solutions of how to design diaphragms, but they're very restricted in terms of their geometry. And one exclusion is they're not applicable to multi-cell box girders, which we had. So we couldn't use these closed form solutions. So the only option we had really was a non-linear buckling analysis to verify the diaphragms. And we spent a lot of time thinking about the best way to do this. Typically, if you had a grillage model, you would have your line beam coming in, and then maybe a refined plate model local to your area of interest, and then a beam element coming out. Now, because we had this as a plate model already, what we decided to do was create a couple of dummy nodes within the global model, and then attach rigid links to each of the nodes on that cross section. Maybe I think it's maybe 2 or 3 meters either side of the diaphragm. And basically we worked out which load case gave us the worst reactions on the diaphragm or on the bearings, and then we created that as a static load case, and then took this model and deleted everything out of it except the bits in between the two dummy nodes. And then we applied the deformations that we'd got in the global model as a prescribed displacement to the two dummy nodes, and applied the traffic loading from that load case to the top of the box girder. verified that we got the same reactions in the two bearings, and then this formed the basis of our sort of refined model. We then refined the mesh in this model and did an eigenvalue analysis. Even so, we did consider doing an eigenvalue analysis based on the global model, but we would have just got an infinite number of web buckling modes, sort of remote from the area we're interested in, that I don't think we'd have ever found the eigenvector or eigenvalue of interest of the diaphragm. And even with this much smaller model, we still had hundreds of web buckling modes that we had to sift through before we could find the buckling mode for the diaphragm that was of interest. But once we'd done that, we were able to undertake a non-linear buckling analysis and verify that we were happy with the results. Okay, I'll talk a little bit about the installation now. So the bridge is being installed on SPMTs, and SPMTs are not static supports. They work based on hydraulic groupings. So I think initially, in the early design stages, I think we maybe had 8 support points. So maybe 1, 2, 3, 4, 5, 6, 7, 8. But it was felt that there was a high degree of statical indeterminacy, and we wouldn't really know what the reactions were at any one of the SPMTs with any great confidence. So through collaboration with the contractor and their SPMT supplier, Mammut, we decided to opt for a 3 support point arrangement. So there's still the same number of SPMTs, but it's just a change in the way they're hydraulically grouped. So you've got a hydraulic group for these ones here, hydraulic group that links these ones here, and then one long hydraulic group along the top here. That you can just see these groups are sort of shown by these wiggly lines. And what that means, you get hypothetical support points here, here, and here. And you've then got 3-point lift, which is statically determinate. Now, I always find these quite hard to get your head around as a bridge engineer who's used to quite static support conditions. But what this means is that when this bridge is lifted up on the SPMTs, the reaction here is equal to the reaction here, but these jacks lift up and these jacks come down to equalize, and that's how you get this sort of theoretical support point in the middle. And this gave us a higher level of confidence in the load effects. Now, it took me quite a while to, maybe I was being a bit slow at the time, but it took me quite a while to figure out how to model these hydraulic groups. But in the end, we just did it through a series of rigid elastic links. So the SPMT supplier was able to give me the details of their spreader beams, and I modelled those explicitly with a small beam connecting that to the superstructure. And then we basically had a series of rigid elastic links that took it to an imaginary support location in between the 2 SPMTs here, and in between the 2 SPMTs here, and in between the 4 SPMTs, the sort of midspan of those 4 SPMTs over here. And then that meant we could model the SPMT lift quite accurately. Now, the reason we wanted to do this is, well, twofold really. The first one is that with the significant amount of magnetite concrete in the ends here, this is actually one of our critical load cases for the cross section in the side span here. It's very highly utilised just over this outer SPMT. So we needed to model it quite accurately. And the second reason is that, again, because of this significant amount of mass concrete you've got in here, we're getting almost 100 mil deflection at the ends of the bridge. And we needed to make sure that there was enough stroke within the jacks of the SPMTs that they could come in, lift it off its existing trestles up high enough so that it can be transported in over the new bearings and then into position. And so we just needed to sort of give everyone that little bit of confidence that there wasn't enough stroke in the jacks and that the deflections could be accommodated. And that wraps up my presentation. So thank you very much, and I'll take any questions now.